and welcome to Accelerating Big Data Analytics Applications with FPGAs and OpenCAPI. My name is Peter Hofstee. I work at IBM in Austin, Texas, and part-time at Delft Technical University in the Netherlands. In this first module of the course, I will try to set the stage and explain, why maybe you should be interested in accelerators and why specifically you should be interested in accelerators that are connected through to the CPU through an interface like OpenCAPI. We will cover 4 different questions. The first is, what is a definition of a better computer? Then we'll go into why we might need accelerators. We'll talk about different ways of integrating accelerators, and I'll end this module with a short lecture on a few accelerator examples. In this first module, we'll look at a seemingly trivial question. What actually defines a better computer? So on this slide, we've listed some of the ways in which a computer might be better. And in the upcoming slides, we'll look at each of them in turn in a bit more detail. So the first way in which a computer can be better is by being faster. Another way is by doing the same problem more efficiently instead of faster. A third way is a computer that is able to handle larger problems. A fourth way might be a computer that is able to handle the same problem with more accuracy. And finally, we'll discuss a computer that is able to do new things. So the first and perhaps most obvious way in which a computer can be better is by being faster. And this matters in a number of different contexts. The first one might be that you're in some kind of competitive situation, and whoever can solve the problem the fastest wins. And the probably most financially interesting example of that is high-speed trading, and we'll talk about that example later in this module. The second one is, when doing a problem fast enough, matters. So this is often called real-time computing. And a good example, I think, is virtual reality goggles. If you are not able to respond fast enough to the inputs and generate the new images, it becomes extremely uncomfortable to wear virtual reality goggles. So the computer has to be fast enough to even make this application possible. Another one may be where it's not really a real-time system, but the turnaround matters. And examples here might be the number of iterations that you can do to optimize a chip design. Another example may be a bank that has only an overnight window to arrange for all the reporting that they need to do on financial situation, basically get ready for the next day. So how do we make computers faster? Well, one is to make computers faster without any change to the programming model and the least amount of burden on the software developers. And to do that, we use faster technology, better circuit design, improved microarchitecture, while maintaining the same instruction set architecture above it. Another way to make computers faster is by introducing more concurrency, parallel computing. This, of course, does place a burden on the software developers, but it's still, somewhat incremental over programming a sequential computer. In many cases, by the way, concurrency is used to do more, rather than to do one problem faster. And doing a single problem faster with concurrency is considerably more difficult than just increasing the throughput. A third fundamental way to make computers faster is to introduce specialization. And this, of course, is the domain of accelerators, where we create, special functions in a computer, or maybe even entire special computers that are specific to a certain task. So let's look at concurrency a little bit more and contrast parallel computing with making a sequential computer faster. So why is it that concurrent parallel computing can often be more efficient? Well, there's this thing called Pollock's rule in the context of microprocessor design. And it's an observation that for many of the microarchitectural trade-offs that we make, there is something called an area times squared equals a constant type observation. And an example is a rule of thumb for the size of a cache. So if I make a cache 4 times as large, my expectation typically is that my miss rate may be cut in half. So if I had a computer that was completely dominated by, the performance of which was completely dominated by the miss rate in my cache, then if I made that cache 4 times as big, my computer might be twice as fast. And that would be an example of Pollock's rule. Of course, this depends on how deep the pipeline is to begin with, or how sophisticated the branch predictor is to begin with. But often in computer design, we operate in this kind of a domain, and Pollock's rule is not a bad rule to have in mind. In contrast, of course, if I have a problem that is trivially parallel, not subject to Amdahl's law, then I can use 2 instances of a processor and do the problem twice as fast, which is obviously more efficient. Another aspect of concurrency, parallel computing, is Amdahl's law. Many problems have a sequential component. A good example, I think, is adding transaction records to a log file in the case of a transactional database, for example. Right. So this log file is used to ensure that the order in which the transactions took effect, and also enables you to recreate the database in case of hardware failure. So if you have such a problem and the sequential part is, say, 10% of your total runtime, whereas 90% of the problem is parallelizable, then even if you speed that parallel part up infinitely fast, you're left with the sequential part, and it only, in this example, only speeds up by a factor of 10x. This means that you have diminishing returns for adding more parallel processing units. And that means that you may be interested in specialization or acceleration for the sequential part. So, even though accelerators like GPUs are used very heavily for parallel problems, there's also, a lot of motivation to use accelerators to speed up sequential computing. So another way in which computers can be better is if they are more efficient. For example, this might be the amount of energy that is used for a certain computation, and that goes to battery life. The most well-known example, of course, is cell phones. You want them to run as long as possible on the available battery capacity. Another example you might care about efficiency is space constraints. For example, if the computation has to live in avionics or some other environment where the available power is constrained, embedded devices, edge devices, far edge is another example. Many of these cases you might not only have limits on battery life, energy, but also on the maximum power that you can dissipate. And Power is also one of the things that factors into the operating cost of a computer. Even in very large facilities that might do their own power generation or have agreements with large grid providers, the cost of a watt year is at the low end typically something like a dollar per watt year, which means that if you have a 10 megawatt supercomputer, you're still paying $10 million electricity bill if you're continuously running that supercomputer. Another way in which computers might be better is when they're able to handle bigger problems. And this might be because they have larger memories, or are larger parallel computers, or if they run faster. One important thing to note is that when you use a better computer to handle a larger problem, you're not quite as affected typically by Amdahl's law. So an example here is, if you're doing a physics computation, which might involve matrix computation, then that scales at a different rate, say n cubed for an n by n matrix, than the communication, which might just be the values at the edge of the matrix that need to be communicated every iteration. So when that ratio between, say, the sequential part and the concurrent part changes with the size of the computation, that mitigation on Amdahl's law is also known as Gustafson's law, who made that observation. Next, I'd like to talk a little bit about solving the same problem, but using a better computer to come up with a better solution to the same problem. So one example, I had the privilege of working on the PlayStation 3, and there, one of our objectives was to replace animation with physics for gaming, right? So this not only made the games more realistic, but also made it much easier to develop games because you didn't have to consider ahead of time, all the action sequences that might happen and animate them. You could just let physics do its work. And another example is in oil exploration, seismic. So, the essential problem here is to reconstruct, what's going on below the surface of the seafloor, based on the reflections that you've received in an array of microphones from some kind of a seismic wave. And over time, as computers improved in their capabilities, the algorithms used to do that reconstruction have changed. So, and there's some examples here. It started with the wave equation migration, and then a more sophisticated algorithm was introduced, reverse time migration, and best I know, the current algorithm of choice is something called full wavefront inversion. So in this case, computers are used to still solve the same problem, but the increased capability of the computer is used to essentially improve the accuracy by which you can solve the problem. So finally, we might use a better computer to do completely new things. Now, the boundary between a completely new thing and an improved algorithm for a known problem, can be somewhat fuzzy. But one way to think about it is that in many cases, when people consider the future of computing, they might think about this in terms of tasks that computers have already been used for. And and if you take that point of view, then considerations like Amdahl's law and other technology limitations might seem quite limiting. However, as we build new kinds of computers and new kinds of accelerators, we can take new approaches to problems and address problems that we didn't address before with computers. And of course, the introduction of neural networks and AI and all the accelerators that are being built currently is a good example of this. For a long time, AI was considered kind of out of reach, for computers to do well on. But a combination of efficient hardware and the availability of a lot of data means that actually a lot of the computer cycles these days go into this new way of computing. And quantum computing in the future, will likely be like this as well. You could try to solve the problems that we solve today with quantum computers, but that might not be the best use of a quantum computer. The best use of a quantum computer is maybe to address problems that we currently don't really consider because they're too difficult. So to summarize, there are many different ways in which computers can be better. They can be faster, have better latency, and they can have better efficiency. They can handle problems of a larger size, or they may be able to, do things more accurately, or even handle new problems. And we've in this module talked a little bit about how accelerators might factor into building better computers, and we'll look at that in more depth in the next module, Module 1b.